In this video, we're going to wrap up chapter 22 by talking about the torque on current loop. Then we'll also look at the magnetic fields produced by currents. So now we're going to look at section 22.8. So in this section, we're going to be talking about the torque on a current loop. And one example that I want to focus on is the example of motors. So generally, we can think about motors as applications of magnetic force on current carrying wires. So basically, this example explains exactly the setup. So you have some amount of current that goes through this loop. So this is a loop of wire. Now the loop has a length L and a width that is given by W. So the magnetic field in this example is going to be pointing from north to south. And the current, so the current on the left side here is pointing up. The current on the right side of the loop is pointing down. So if you use the right-hand rule, if you know the direction of the magnetic field, and if you know the direction of the current, you can determine the direction of the force on the left side of this loop. So the force on the left side is going to be pointing into the board, into the paper. The force on the right side is going to be pointing out of the paper. So because you have two forces equal in magnitude, but the point of the application of the two forces is not the same, so these two forces are going to produce a torque that is going to cause this loop to rotate about this axis. So basically what this is happening is that you're taking the electrical energy from the current and you're and this electrical energy is being converted to mechanical energy by means of the magnetic field. So some applications of electric motors are things like an electric washing machine, fans, air conditioners, refrigerators, and so on. So these are all appliances that use magnetic fields to convert electrical energy into mechanical energy. So now we're going to derive an equation that is going to let us calculate the torque on a current carrying loop. So again, if you look at this picture right here, so you have a loop, and this loop carries a current, and it's placed in a magnetic field such that this is the north and this is the south. So the magnetic field is going to always point from north to south. Now the presence of this magnetic field is going to produce forces that are going to act on the left and the right side of the loop, and this will generate a torque that is going to cause this loop to rotate inside the magnetic field. So what you see on the left side here is just different orientation. So these are like snapshots. So as this loop is rotating inside the magnetic field, the orientation is going to change. So this is like the general orientation right here where the magnetic force is going to be pointing at some angle. In this example right here, this is when you have the maximum value of the torque. So here the force, so the loop is oriented in such a way that the force is at 90 degrees with respect to the magnetic field. Then in this orientation right here, you can see that the forces are pointing in opposite directions and also at 90 degrees with respect to the magnetic field. So in this configuration right here, the torque is just going to be equal to 0. So I can put all of this together and derive an equation that is going to let me calculate what the torque is. So the torque is given by this equation. So N is the number of turns, I is the current, A is the cross-sectional area, which is just the length times the width. B is the strength of the magnetic field, and theta is the angle between the perpendicular of loop and the B field. So, so the perpendicular to the loop is a vector that points at 90 degrees with respect to the surface of the loop. So if we look at this equation here, we can see that, for example, when this angle, when the angle is equal to 90 degrees, then the sine of the angle is just equals to 1. So that's when you have the maximum torque. When the angle is equal to 0, the sine of 0 is equal to 0. This is when you have the minimum torque. All right, so now we're going to look at one example on how we can apply this equation to calculate the torque. So this is example number 22.5. So we're going to calculate the torque on a current carrying loop that is placed in a strong magnetic field. So right here is asking us to calculate what the maximum torque is, and it tells us what the number of turns is. It's 100 turns. And it gives us a square loop of wire that has the length is 10 centimeters, the width is also 10 centimeters, and the magnitude of the current is 15.0 amps, and the strength of the magnetic field is 2.0 teslas. So I know that if I want to calculate the maximum torque is when the angle is equal to 90 degrees, and when theta is equal to 90 degrees, sine of theta is just equals to 1, and so I can calculate the maximum torque using this equation. So in this equation, N is just the number of turns, I is the current, A is the area, and B is the strength of the magnetic field. And so if I plug everything into this equation, I end up with a torque that is given by 30.0 Newton meters. So this is a large enough torque that can be useful to generate mechanical energy from the electrical energy. All right, so now we're going to move on to section 22.9, and this is talking about magnetic fields produced by currents. So basically, we're trying to understand exactly where does magnetic fields come from. So we can produce a magnetic field from a wire. So in this example, you have a wire that carries a current, and the current is moving in the upward direction. And so for the case of a wire that is a very long straight wire, the strength of the magnetic field can be calculated using this equation right here. So it's just mu naught times the current divided by 2 pi times the radius. So the radius is the distance from the wire, I is the current, R is the distance from the wire, and mu naught is the quantity that is given by 4 pi times 10 to the negative 7 teslas meters per amps. So this equation is only going to work if we assume that the wire is a straight wire that is very long. And we notice that the magnitude of the field only depends on the distance from the wire. So again, if you think about this equation right here, you can see that the strength of the magnetic field is going to reduce as the distance is going to increase. So for example, if you calculate a magnetic field at a distance that is 4 centimeters from the wire, you expect to get a value that will be 4 times smaller than at the point that is 1 centimeter from the wire. So again, if I calculate my magnetic field at this point here, it's going to be larger than the magnetic field at this point. So as you go further away from the wire, the strength of the magnetic field is going to reduce. Now this equation tells me how I can calculate the magnitude of the magnetic field. If I want to get the direction, I'm going to use the second right-hand rule. And basically what the second right-hand rule says is that if you place your thumb in the direction of the current, and then you use your fingers, you just wrap your fingers around. So place your thumb in the direction of the current and wrap the rest of your fingers around this wire. then it's going to tell me the direction of the magnetic field. So in this example here, you can see that the magnetic fields are circles around the direction of the current. So these are just magnetic field lines that are pointing in this direction. So this would be in the counterclockwise direction. So for example, if the current is going up, the magnetic field is pointing in the counterclockwise direction. If the current is pointing down, then the magnetic field is going to be pointing in the clockwise direction. So now let's look at one example here. So this is example number 22.6. I want to calculate the current that is needed to produce a given magnetic field. So for example, we assume that we have a very long straight wire and want to calculate, for example, what amount of current do I need to produce a magnetic field that is twice the strength of the Earth's magnetic field at a distance of 5.0 centimeters from the wire. So we know that the Earth has a magnetic field of about 5.0 times 10 to the negative 5 Teslas. So since we want the magnetic field to be twice that value, so we need to multiply this by 2. So if you multiply that by 2, you get 1.0 times 10 to the negative 4 Teslas. Now, so using this equation, I can calculate what my current is. So if you rearrange this equation, we know what the distance is. So the distance is just the 5 centimeters, which you can convert into meters as 5.0 times 10 to the negative 2. The B value is 1.0 times 10 to the negative 4. And then if you substitute this mu naught, which is 4 pi times 10 to the negative 7, then the current is equal to 25 amps. So we need a current of 25 amps to produce a magnetic field that has a magnitude of 1.0 times 10 to the negative 4 at a distance of 5.0 centimeters away from the wire. All right. So in the previous example, we assumed that the wire was a straight wire. But now what if we have a wire that looks like a loop, like a circle, like this? So again, the current is going to come in like this, and then it goes around like a circle, like a loop. So in this case, there is an equation that is going to let us calculate the magnitude of the magnetic field at the center of the loop is given by mu naught times I over 2 times R. So again, in this equation here, I is the current, R is the radius of the loop, and mu naught is just equals to 4 pi times 10 to the negative 7 Tesla meters per amps. Now, this example, we're looking at just a single loop, but what if we have n turns of wire? So for example, I'm not just having a single loop, but I'm taking a wire and I'm wrapping it around such that I can generate n loops that are kind of stacked on top of each other. Then I can calculate the magnetic field as n times mu naught times I over 2 times R. So again, just by increasing n, I can increase the magnitude of the magnetic field. So again, this equation will give me what the magnitude is. And then if we want to get what the direction is, again, you use the right-hand rule. So you place your thumb in the direction of the current, and then you wrap your fingers around the wire. It tells me what the direction of the magnetic field is going to be. So as you can see in this picture here, so this will be the magnetic field lines that are pointing out of the loop as the current flows through the wire. Now, another example that we're going to talk about is the magnetic field that is produced by a current carrying solenoid. So again, if you remember, we explained about what a solenoid is. So again, this is an example of an electromagnet. So when you run current through this loop, it's going to generate a magnetic field, and the magnetic field is going to be pointing in this direction. So we can calculate the strength of that magnetic field by using this equation. So B is equal to mu naught times N times I, where mu naught is the value that I've given you before, I is the current, and N is the number of turns, which is the number of loops per meter. So this is an example that we can look at this example here. So basically, again, we're just trying to calculate the strength of the magnetic field that is produced by a given solenoid, and it tells us what the number of turns is and the current. So if you solve that, you get a B value of 2.0 Teslas.